I'm Amber Camel. I'm the project manager for the project, and Jeff Basara is going to be giving our webinar today, Extreme Drought to Extreme Rainfall, Mechanisms that Produce Heavy Precipitation in the Great Plains. And with that, I'm going to let Jeff take over.
Good afternoon, everybody. My name is Jeff Basara, and I'm the official guinea pig. I'm at the School of Meteorology at the University of Oklahoma, and I'm also at the Oklahoma Climatological Survey at the University of Oklahoma. And as Amber alluded to, we had a conversation of what would be a nice kickoff topic to sort of get the webinar series underway, and this topic came up, and partly this topic has come up for a couple of very important reasons, which I'll get to here in a minute. But I'm not sure the background of everybody who's participating, so I've kind of made this a general overview type of webinar that'll kind of get things rolling today. If we need to get into more details at some point in the future, we'll probably come back to some of these topics in a more detailed manner here in the near future. But of course, always want to acknowledge our important people that helped put this together, and I want to share thanks with Mark Schaefer at the Southern Climate Impacts Planning Program. We share slides, and I've got some of his slides in this particular presentation. Also, Jordan and Katie Christian, they are former students of mine, and unfortunately they are gone. And I said unfortunately because they're great students, but fortunately for them, they're working on their graduate degrees now at University of Wyoming, and working on advanced degrees in weather and climate. Also, I can't forget to acknowledge the Agriculture and Food Research Initiative Competitive Grant, the NIFA grant that has provided just a significant amount of funding for this project, but also the NOAA Climate Program's SARC program grant also has contributed to this type of work, and by merging these two sponsors and their funding towards these types of projects, we've really been able to sort of start driving new insights into how weather and climate impact certainly socioeconomic sectors beyond just the typical weather-climate water interface. In this case, beef cattle production. So one thing I wanted to really kind of begin to highlight is if you take a look at this particular map that I've shown, this is a precipitation map for the month of May from the year 2012. And so it might be a little bit hard to see, and I'll try to annotate this as best I can. Let me get my annotation pen. So if we were to sort of look at the Southern Great Plains, this area sort of bounded here is the Southern Great Plains of the United States. Maybe I should pick a better color. Actually, I don't know if any color is going to work really well on this, but the Southern Great Plains of the United States, basically that portion of the region for east of the Rocky Mountains, downward, southward to the Gulf of Mexico, and extending on into the sort of the Ozark Plateau. This region is home to a lot of beef cattle production, and maybe future webinars will get into some of those details of just how much. But in this particular analysis, we see that rainfall and precipitation for that particular period of May 2012 had significant deficits on the order. In some locations, precipitation was only 5, 10, 15, 20%. And so this is for an entire month of May, and it's a significant period of time for precipitation across the region. And yet at the same time, if we move forward, we can also see in that exact same region for 2015, this year, there can be tremendous amounts of rainfall that occur. And in this case, in 2015, there are some locations that are certainly well above 100% or the normal precipitation in the 2, 3, 4, or 600% rainfall totals. And notice how large of an area this expands across the entire, most of the Southern Great Plains. So sort of the question becomes is, how do we go from one year where significant deficits occurred, of course, 2011, 2012, really significant drought years. And so there were, that deficit in 2000, the previous deficit here in 2012, really coupled with what happened later on, not just in the Southern Great Plains, but most of the heartland of the United States in terms of a significant drought that developed. And yet at the same time, in a year like this, have significant amounts of precipitation, very beneficial rains, and in fact, beyond beneficial into the flooding category, and had some adverse impacts in that regard. How do we end up in these types of precipitation regimes from one year to the next? So that sort of was the motivation for driving this particular talk today, and that's what and that's sort of the how we're going to proceed. So I want to give you a little bit of a background, though, and sort of pick on the state of Oklahoma. We end up with, this is sort of the climatology of precipitation in Oklahoma. And what's really important about the Great Plains of the United States is that these individual dots that are all plotted are individual years going back into the late 1800s and into 2000 through 2014. If you look at these dots and then compare them, there's an average line that's there. In this case, for the state of Oklahoma, about 33.6 inches of rainfall per year, averaged across the entire state. But notice that very few of those dots actually fall on that line. Many of them are either well above or well below. And so what's fitted on here is a 5-year running average. And areas that are highlighted in green are the periods of time which represent above that mean, above normal types of precipitation. And areas below that in the brown are longer term periods of below normal or below the mean precipitation. So a couple of things to point out here on this particular graph is that there are some areas of significant drought in terms, certainly this period of the 1930s, which I'm highlighting. That period of the 1930s is the Dust Bowl period. And that was followed a number of years later by a decade later or so of the very significant drought of the 1950s. And then more recently, we've been experiencing drought in Oklahoma during basically the 2000 teens. If I sort of clear that, you'll also notice that there's significant above normal precipitation periods. And this period in particular that's highlighted with the red circle represents basically 15, almost 20 years of above normal precipitation that has occurred more recently in across Oklahoma. In fact, what's interesting about this particular period is that basically this entire window, it almost represents a generation, so to speak, of people. So for a number of our younger people, they did not, and certainly people that are in the age of 30 or below, really didn't have a good grasp on what drought of the Dust Bowl, these dry periods of the Dust Bowl in the 1950s were like until recent years when we've had some pretty significant drought years. Notice, though, that there's basically, there's other periods. In fact, the 1940s have a significant above normal precipitation period. And by the way, we call these pluvial periods. So tend to be drought periods, and these green periods are what are defined as pluvials or above normal precipitation. You notice that we don't really talk about the pluvial of the 1940s as much as we talk about the drought of the 1930s and 1950s. And yet the pluvial periods are really critically important to overall water resources in the region. And it's usually during these pluvial periods that we see significant agricultural production. People get used to having abundant rainfall around it, and then, boom, we get hit in the region with significant drought, and that has important impacts. Now, it's not just Oklahoma that experiences these features. If I move to another region and just pick a climate division in North Texas, you basically see the same thing up here. So those periods of drought to some degree. Some in some cases like this are relatively stronger or weaker, and same with the pluvial periods. But notice that variability from year to year exists. And I also want to point out, maybe I should point out this on the North Texas one, but you'll see it also in the Oklahoma analysis, is this particular period that spans 1956 and 1957, and this dramatic change that happened between the 2 years. We're going to come back to that because that was also an impetus for some research that I'm going to try to highlight a little bit of in this particular talk. And this is what we call a dipole between drought and above normal precipitation. So in this case, a significant transition from drought to above normal precipitation. This window of time, 1956 to 1957, took in the state of Oklahoma, it took Oklahoma from significant drought to its wettest year on record. So this is a really important period of time. But if you look carefully, you see these types of trends throughout these time series timelines. So that's North Texas. Let me clear that. Move on and show Western Kansas. And again, you see these types of periods that exist with drought periods and pluvial periods. So when you look at the Great Plains as a whole, what I'm trying to sort of communicate at the very beginning here is that you see the significant variability. And if you look at the Great Plains as a whole, you see these patterns showing up throughout the Great Plains. And so really want to get that sort of as a groundwork that this is an important component of our research. And also notice this variability and these dramatic changes that happen from year to year. Very few periods of basically normal types of precipitation. So what we really should be expecting is not normal precipitation, but some direction one way or another from the mean, from the normal. So just kind of taking a step back, what is weather and what is climate? I know that, again, I don't have a good handle on the backgrounds of everybody, so I want to just sort of get everybody on the same page. Weather is that condition of the atmosphere at any particular time and place. So right now, I'm sitting in my office looking out the window here in Norman. The weather is beautifully sunny, and it's actually not too hot out there. It's a great day. And this is the day-to-day state of the atmosphere. And it may rain tomorrow, and it may not. Probably won't. Probably be another beautiful day just like this. Now the climate, on the other hand, is sort of the synthesis or the accumulation of all these daily and seasonal weather events over a longer period of time, weeks, months, years, and decades, millennia. How the climate is definitely that sort of synthesis of all those events. And it includes weather. And includes extreme events. Could be heat waves, cold spells, could be really significant precipitation events, either drought on the dry side, or these what we've seen this year in the southern Great Plains with abundant rainfall across a large area. And so these long-term, and it's also, the climate is also a function of these long-term averages. So we can average these things. We can get an idea of what would be the typical or the normal or something along those lines. But in some places, normal represents something that's, that you could expect from year to year. Normal is a little bit more difficult in terms of the Great Plains. As I just showed you, in terms of precipitation, there can be large swings from year to year. And that creates a little bit of a challenge when trying to communicate what's normal in the Great Plains of the United States. And so that's why we tend to try to capture and highlight these departures from normal of these weather variables, put everything into perspective. Now that's the great thing about the normals or the means, is that they can at least give us a baseline of where would we normally be at in terms of our climate, and how far from in one direction or another are we. Now, what I'm really going to highlight today is some of the seasonal interannual variability. And it sort of falls in between weather and climate, because it's not on a daily scale. And we're certainly not averaging up over years to decades. It's really that window in between. But at the same time, it includes very important features such as droughts and pluvial periods that can develop, especially the development and the change of those types of periods happens in this seasonal interannual variability. So the main question here becomes, what causes the variability, and what takes us from when we compare two different Mays in the last couple of years, like 2012 and 2015, what causes that variability in precipitation? Well, what I've got highlighted here are the 30-year normals across the lower 48 of the United States of, in the upper left, the mean annual temperature, and in the lower right, the normal precipitation accumulated over it each year. And what's really important in terms of the Great Plains, and I sort of highlighted these boxes, is if we look at the temperature analysis, you see that the average temperature increases from south to north, basically these east-west oriented lines of temperature. So it's warmer in the south and it's cooler in the north. I don't think that surprises anybody. But what's also important is if we look at the precipitation part, there's this really strong, what we call gradient of precipitation from east to west across the Great Plains of the United States. Very, very impressive gradient of precipitation, where there's on average over 50 inches of rainfall that will fall in the southeastern portion of the plains, and in the western portion of the plains maybe a foot or less. So there's a significant transition zone in terms of the overall amount of precipitation that we would expect to see in any given year. Now, what's also interesting is, if you look out to the west, you see these gradients of precipitation, but mainly those are driven by terrain. Yes, the Rocky Mountains do occur, and we're looking at this region, but really the precipitation gradient in the Great Plains is mainly in the absence of significant terrain features, and is a product of a very large number of different types of processes, some of which we'll highlight here. What's also interesting is the orientation of these gradients. So the precipitation gradient is east-west oriented, whereas the temperature gradient is north-south oriented. This also creates a large amount of biodiversity across the Great Plains, and so it's generally warmer, and with more precipitation in the southeast portion of the domain. And if you go down to eastern Texas and western Louisiana, there's a lot of swamp, and I mean it's a warm, humid location. Whereas when you get up into the high plains, especially into northern Colorado, or into Colorado and Nebraska, that region is a much cooler type of climate with a lot less precipitation. But keep in mind these orthogonal gradients of temperature and precipitation. It's a main driver and contributor. And you can kind of think about it this way. So if we're getting into what causes these extremes, one of the extremes is just simply this. With such an east-west oriented precipitation gradient, any subtle shift in that precipitation gradient year to year caused by any feature in the atmosphere is going to have an impact. And for example, if I clear this and just we focus in maybe on this dot right in the middle, where say that's El Nino. El Nino on average gets about 32, 33 inches of rainfall per year. A subtle shift in one direction, like this year, may give, in which this precipitation gradient was shifted, say, back towards the west, may bring 40 to 50 inches of rainfall into El Nino in any given year. Otherwise, there could be a shift. Some atmospheric processes or larger scale global processes could shift the precipitation further to the east and basically shift that gradient further to the east. Now brings El Nino into a region and into a zone where they may only receive 20 to 25 inches of rain per year, and that can have significant impacts. So this natural gradient in precipitation is a real key driver to the overall processes. And again, now we start getting into the questions, what creates the gradient in the first place? And I'm not sure we'll get to all those answers at this particular point in time on this particular day. There's a lot to be learned still. So what I want to highlight a little bit here first, and we'll come back to this talk, but or this study, but there was a motivation to understand these rapid changes, these drought to pluvial dipole events that we've been seeing. And a good example was that case from 1956 to 1957, where it was a significant drought year and followed by the wettest year on record. How does that happen? What are the mechanisms that would cause that? But before you can even get to that, the question was sort of how often do these types of events happen in the Great Plains? And so there was a study done by Jordan and Katie and myself, and we looked at this. We were really curious. How often do these types of rapid swings happen where you can be in the middle of a drought in one year and end up with exceptional amounts of precipitation on the other side of that mean bar in any other given year? So we divided up the Great Plains into three different subdivisions: the Southern Great Plains, the Northern Great Plains, and the High Plains. And getting into the logistics of that, if you want to follow up later, we can have a discussion about that. But these are the three areas that we wanted to look at and sort of subdivide the Great Plains into. And we'll come back to this talk, but I also wanted to point out in terms of the climatology, and from an agricultural perspective, I've often been told by agricultural producers, it's not just how much rain you get, but it's when you get the rain. And so this graph just sort of highlights the annual precipitation. It starts with it's a water year analysis, so it starts in October and ends at the end of September. But you can see that the peaks in rainfall basically occur in the Northern Great Plains and the Southern Great Plains and in the High Plains, basically in this April to May to June window, highlighted here. So that's when we typically expect to see the majority of the precipitation. Now, the Southern Great Plains receives more precipitation than the Northern and the High Plains, which is not unexpected. It's a little bit closer to a major source area for atmospheric moisture, namely the Gulf of Mexico, although the eastern tropics of the Pacific are also really important in terms of bringing moisture into the Southern Great Plains and into the Great Plains in general, as well as moisture off the Atlantic. Notice that the period of December, January, February tends to actually be the least amount of precipitation, although sometimes it feels like that's in the summer. I think that gets a little more complicated by the fact that it's just so hot in the summer. We really would like to see rain, and we generally see quite a bit of rain averaged over these domains in the summertime, even though it feels sometimes like we're not getting much. And of course, that varies significantly from one year to the next. Now, one of the main other contributors is just what we call there's basically a subtropical high that develops over the Great Plains during the warm season months. So following the spring rains in April, May, and June, sometimes if you're around this particular building, the National Weather Center, you'll hear our students refer to this as the Death Ridge. So a large dome of high pressure, not just at the surface, but through the mid layers of the atmosphere develops. It tends to become a very inhospitable environment for precipitation. Air descends. There's little cloud formation, lots of sunshine, gets nice and warm. And generally, it's an inhibitor to significant amounts of cloud formation and precipitation. And that's pretty typical. If you actually look at the annual climatology of the region, especially the Southern Great Plains region, we generally see this feature begin to set in about the middle of June and last through September and into late August. Of course, year-to-year variability exists. In some cases, this feature can be really strong. Years like 2011, 2012, very strong ridge developed not just at the surface but through the depth of the lower and mid-atmosphere, and we had very little rainfall across the area and significant drought formation. Years like 2007 saw quite a significant weakening of this feature and allowed a lot more precipitation to develop throughout the entire summer month. And so this feature tends to be quasi-stationary, tends to not move too much during the summertime, but there's a lot of year-to-year interannual variability that in terms of its strength and intensity and location. And all of those features are important in terms of how it affects precipitation. just sort of reminder as I get into sort of the next portion of this topic. Hopefully I'll see this. It's a little hard to see and do the presentation at the same time. But if you do have questions, go ahead and type them in the comment box, and I'll try to get to them as I'm going along. But again, feel free to ask questions at any particular point in time. But getting back to the webinar, in a sense, one of the impacts of precipitation in this region, believe it or not, rests in ocean circulations that can be half a world away. And ocean circulations can and really are critically important for not just our weather, but global weather and climate. And what ends up happening is sea surface temperature, like the atmosphere, doesn't stay the same. It oscillates, it changes, and there can be times where the water temperature is a few degrees warmer or maybe a few degrees cooler. And it goes through phases, warm and cool phase. There are a number of different types of oscillations that we see in the ocean. Some can be in the Atlantic and Pacific, can be every 20 to 30 years in terms of going between some of these warm and cool phases. But in terms of the tropics, what we see sometimes are rapid changes, or much more rapid, and some interannual types of variability. And in particular, El Nino and La Nina, which can last on the order from 6 months to to a year or two, have also significant impacts on atmospheric circulations. And what ends up happening is these sea surface temperature anomalies, they feed back to the atmosphere. They serve as a memory for the atmosphere. And by doing so, they can affect the entire global circulation and that sort of that jet stream pattern that we see, the storm track, if you will, of larger scale cyclones and anticyclones. And so these sea surface temperature anomalies are important drivers in not only wet periods but also dry periods. And so just kind of looking at El Nino and La Nina, just a couple of simple graphics that sort of point this out. And when there's a warming of the equatorial waters in the Pacific, that's an El Nino type of event, and it brings the subtropical jet into Southern California and strengthens that subtropical jet and brings a more abundant moisture in a storm track that's much further south into Southern California, and then it can also influence the southern and southeastern portion of the U.S. Whereas La Nina tends to be a little bit different. The ridge tends to develop a little bit stronger over the Great Plains. It tends to inhibit precipitation. Now, these types of events generally for the Great Plains are associated with a warmer, wet type of pattern and El Nino types of events, and a drier pattern in La Nina types of events. Of course, the strength and the intensity of these El Nino and La Nina events also matters. So the stronger the El Nino or La Nina, the more likely to see a significant enhancement of atmospheric processes in the Great Plains. So if they're weaker events, or what we call neutral types of events or near neutral types of events, they may not have significant impacts. If they're strong events, then there may be greater impacts. But when looking at the broader picture of what impacts weather and climate in the Great Plains, these features can be pretty important, especially when we start looking at, from one year to the next. What's causing this variability? Well, certainly we need to take a look at these sea surface temperature anomalies from year to year that impact the weather and climate from year to year. Now, again, it's a little bit more about El Nino and La Nina. As mentioned, it really does have it tends to have an effect on just the overall global circulation and the storm track. And, in La Nina, it affects that the jet, stepping back for a second, in general, these types of effects tend to also take place more towards the winter months or the cool season months, because that's the point at which the the overall storm track tends to be further south, and in the summertime that storm track naturally shifts further to the north, and so processes that are happening in the equatorial regions aren't as likely to be coupled to something that happens in the mid-latitudes where we live. Whereas in the wintertime and the cool season months, the storm track shifts much further south, and so there can be that connection a little bit stronger between the equatorial areas and the mid-latitudes. But in terms of Oklahoma, it tends to have a moderate relationship, and the further south you go and southwest into the Great Plains, that's when we start to see the more significant impacts of these types of events due to equatorial water warming or cooling as a function of El Nino or La Nina. Incidentally, also, I should have probably mentioned, I think I went a little too fast in terms of my slide, but one other important point is that these types of processes that develop in the cool season, for example, if we have a dry winter and spring, that can also affect what happens in the region. So if there's not a whole lot of water that falls from the atmosphere, it doesn't moisten the soils, and that can have a feedback process that builds on top of itself, like in 2011. 2011 was a La Nina year, not a lot of rainfall in the winter and into the spring. That set the table, especially in the southern Great Plains, for dry soils, which then continued through the spring and into the summer, and just enhance that whole process. So these features, while they may not be as strong in the summertime, they can lead into a different type of pattern that can perpetuate through the summer months. So just kind of looking at this graphically, what are the correlations? So the correlations between what's happening in the equatorial Pacific and regions of the U.S. So in general, these are the precipitation correlations, meaning if there's something going on in the equatorial Pacific, what's its correlation to the precipitation, whether it's greater or low or less. So these are sort of some of those correlations, and basically there's positive correlations year round, especially in the winter and the spring in these top panels. So what we're looking at is positive correlations. So if there's warming in the equatorial Pacific, we generally see more precipitation that occurs across the Great Plains, especially the southern Great Plains, in this the June, July, August period. But also, if we look at some of these other variables, this is the top left is December, January, February. The top right is March, April, May. And so if there's an El Nino type of event going on, we generally see more precipitation in this domain across the Great Plains. And it's most significant in that December, January, February window of time. And that can actually change even in an El Nino event in the September, October, November. We sometimes have a little bit of a drier period during that window of time where it's there's a negative correlation, and during that type of period, but rapidly becomes a positive correlation as we get more into the winter months. And so again, you also see that the stronger correlations, especially with El Nino, tend to be towards the southern portion of the United States, and so further south into the southern Great Plains has a more likely impact of these anomalies in sea surface temperatures. And El Nino and La Nina itself can be pretty variable. So this is the Multivariate Index, so the sort of the phases of El Nino and La Nina. So the blue blue portions of this graph are La Nina types of events. So basically the cooler than normal sea surface temperature anomalies, whereas the red values going back from 1950 through 2014, the red ones are El Nino events. And you notice that they last, some of these, they basically last on the order of a year or two in terms of some of these stronger features, although the La Ninas can tend to last a little bit longer than the El Nino events. And notice that the El Nino events can also be a little bit stronger than the La Nina events in terms of overall magnitude, but just a little bit more short-lived, although in the case of there was a long-term El Nino that basically stretched from 1990 to 1995. I want to point out a couple of El Ninos, the 1982, 1983 El Nino and the 1997, 1998 El Nino. They were both real significant El Ninos, very strong El Ninos, and had significant impacts on the global, basically global weather patterns. And for example, significant precipitation in California, that creates obviously hazards such as mudslides, but also when there's strong El Nino events like this, places like in the Indian monsoon tends to weaken, so they end up while locations in the U.S. in the southern U.S. end up with abundant rainfall, places like the Indian subcontinent can end up with significant rainfall deficits and can lead to drought and famine. So this is sort of a perspective, a look at the seasonal interannual variability of El Nino, La Nina. One of the more recent La Nina events that was significant was here in the basically 2011 to 2013 timeframe, which also brought significant drought coincided with significant drought in the southern Great Plains and the central plains of the United States. And there is certainly significant correlation between those types of events. So El Nino, La Nina tends to be one of those drivers that can have a significant impact on precipitation across the Great Plains on these time scales that are a little bit longer. Now, I have to mention this since we're talking about El Nino, La Nina. Some of you may have heard that we are anticipating a Godzilla El Nino. And it's sort of funny how that term came about. It was actually mentioned by a NASA scientist at the Jet Propulsion Laboratory, and it was really made in reference to what the impacts could be for California. What's happening right now is we are in an El Nino period, and it's been an El Nino that's been strengthening with time. So if we look at this, this was recently released by NOAA, this particular plot. I'll draw this in here. Where are we right now? Well, we're basically here in August, so this is the most recent data. So everything to the left of that blue line that I just drew, going back a number of months, so August, July, and so on, is above this zero line. So those are all showing that a warmer than average sea surface temperature anomalies in the eastern tropical Pacific. So that's consistent with El Nino. And notice that with time, it's actually been strengthening. And it's gotten to the point now where it's become a pretty significant El Nino event in terms of the magnitude of the sea surface temperature anomalies. And so over here in the graphic to the right shows where this warming, so these are anomalies in sea surface temperature, and the greatest anomalies are occurring in the tropical Pacific, but also extending on up into these are forecasted anomalies of sea surface temperature moving forward. But this would be consistent with what we have been seeing. But these are the forecast anomalies of that sea surface temperature extending basically September, October, November, November, December, and so on into the future. And what's interesting is this pattern persists. So November, December, January, pretty strong El Nino. So what's actually forecast to occur is a continuous strengthening of this El Nino basically into the wintertime. And the impacts of that would put it on the order, if that were to occur, it would be on the order of those 1982, 83 El Ninos, 1997, 98 El Ninos. So a real significant type of El Nino events that could have global impacts in terms of overall magnitudes, in terms of who gets abundant precipitation, who doesn't get abundant precipitation. We've already seen this year a weakening of the Indian monsoon. And so they haven't actually gotten as much rainfall as they normally get in portions of India. They're entering drought phase right now. And we've certainly seen an enhancement of some precipitation in the southern portions of the U.S. And certainly that could be in part tied to El Nino and the early onset of this El Nino. The question is what's going to happen as we go into this winter. So what's going to it's very likely that you'll hear more and more about El Nino as we move into the wintertime. What does that mean for us here in the Great Plains? It means a better likelihood that we'll see above normal precipitation. If you live in California, there could be significant precipitation, which on the tail end of the drought that they've been dealing with could be really important in terms of their overall water supply, but it also could have some pretty significant effects and impacts from a socioeconomic standpoint. So sort of moving forward, there's more. It's not just El Nino and La Nina that matter. I sort of mentioned that from the onset. Some of these circulations are a much higher frequency. Some are lower frequency circulations. Higher frequency circulation is called the North Atlantic Oscillation. It can actually, there's pretty significant interannual variability associated with it. And it has impacts on the northeast, sort of the northeast portion of the U.S. and into Europe. And if it's negative, it tends to be towards dry in the southern plains. Of course, sometimes its impacts are masked by other processes, say El Nino. Maybe it's got El Nino is having can have a more dramatic input on our climate system than, say, the NAO or the North Atlantic Oscillation. There's another oscillation called the Pacific Decadal Oscillation. This one tends to be longer term period, on the order of decades. Hence the name Pacific Decadal Oscillation. And if you notice that over here to the right, that basically this time scale shows these features to be these cool regimes and warm regimes lasting on the order of 20 to 30 years. So periods like the 1950s often are a period of record in terms of drought of the 1950s is often tied back towards the Pacific Decadal Oscillation. And we see that this periodicity, that the sort of warmer and cool phases of the Pacific Decadal Oscillation can last a whole lot longer than some of the features like El Nino and La Nina. And then there's also the Atlantic Multi-Decadal Oscillation, which is even also has a longer term frequency associated with it. It's basically has a warm phase that's usually dry for the southern Great Plains, a cool phase that's a little bit wetter. And it can, in fact, also impact the hurricane season. And so more intense cyclones or less intense cyclones depending on which phase it's in. So there are all these different types of sea surface temperature anomalies. Some are smaller time scales and some are larger time scales. And the interaction even between these sea surface temperature anomalies and the locations of them can have impacts. For example, here's just an example of when the PDO and the AMO align, it can be bad news. In fact, these periods tend to be when we have some of our more significant drought periods, when the AMO is a positive phase and the PDO is a negative phase. So this becomes really important in terms of, again, trying to identify what's driving our local climate, and not only from a decadal perspective, but on a year to year. So these sea surface temperature anomalies can be pretty important. But it's also important to consider what's happening more locally. So sea surface temperature anomalies represent sort of a memory of the land of the ocean surface to the atmosphere, but that's the same type of thing can happen in the southern Great Plains from the land portion of the atmosphere, having its sort of impact on the overlying atmosphere and providing feedbacks between the surface and the atmosphere. And so what ends up happening if there's abundant moisture from precipitation, you have abundant vegetation, there tends to be more evaporation, and that can have a recycling effect. If there's abundant evaporation, that can actually lead to more clouds, more precipitation, which then moistens the soil, leads to more vegetation, and you get this positive feedback that develops between the surface and the atmosphere, leading to increased precipitation. 2015 is one of those years that sort of has that signal. Other recent years, certainly in central Oklahoma in 2007, had this feature of land-atmosphere coupling leading towards sort of a positive feedback between precipitation and evaporation. Now the opposite can happen too, where the soil dries out, and so there's very little evaporation, so all the sun's energy then goes into heating the surface. And in those scenarios, what ends up happening is that we end up with a drying of the atmosphere, which then with a drying of the atmosphere leads to no precipitation, no clouds, continual drying, and you end up with a negative feedback. And certainly years like 2011 and 2012 have that signal associated with it, where dry begat more dry, so to speak. Now, there have been a number of studies that have sort of shown that there is this important signal between the land surface and the atmosphere, and it just so turns out by this one, and this one that was published in Science by Randy Koster, that the Great Plains region has one of these strong, very strong signals of coupling between the land surface and the atmosphere. So the state of the land surface really is important in terms of what's going to happen from a precipitation standpoint. So if the state of the land surface is moist in the spring and into the early summer, then it's more likely to have enhanced precipitation continuing into the summer months. Whereas if it starts off dry, it's much more likely that you're going to end up in sort of a dry circulation type of pattern. And this was looking long-term. More recent study has also sort of highlighted these events, but then also shown that this coupling can exist and sort of changes in the domain from year to year. So there's some interannual variability of this coupling strength as well. And that, of course, all of these things complicate just how much rainfall falls in your backyard. But there is this sort of important feature of the land surface and its state and how it impacts the atmosphere. So there's large-scale processes that are associated with sea surface temperature anomalies, but then also the landscape itself has that same type of memory to the overlying atmosphere, and then that feeds back into the local precipitation. Now, an example of that, and I've already sort of alluded to it, was this particular feature that happened in 2011 across the southern Great Plains with really intense drought that developed, and then there was a thermal anomaly. It got really hot in the southern Great Plains, and all sorts of records were broken in terms of the total number of days above 100. Oklahoma City, I never thought in Oklahoma City that we would break our record of 50 that was set in 1980. And of course, in 2011, we had 63 days of 100 degrees or more. By contrast, this year in Oklahoma City, I believe we're at 3. And so, whereas the average, I believe, is 5. I'd have to go back and double check those records. Don't quote me on that. I'm like a good climatologist, but in general, these patterns of what happens in the land surface, especially in the springtime, does have an impact on the atmosphere later on and through the warm season months. Of course, that's really important when we get into the vegetation, the forage, and how that impacts something like beef cattle production. Now, sort of as that alludes to the fact that there's, how do we deal with some of these features? So a long-term drying pattern would be drought, and how do we measure and monitor drought? Well, we can do that with a number of different indices that are out there. We can look at departures from normal in terms of rainfall. There have been a number of other indices like the Palmer Drought Severity Index or the Standard Precipitation Index, basically looking at some of the anomalies in precipitation, how it affects, and the duration of those anomalies. We can also use something like soil moisture, and unfortunately we don't measure soil moisture very well on a real-time basis or across the region, across the United States. We just now got our first satellite SMAP that is supposed to really do that across the globe, and so, but yet we know that soil moisture is that critical link and feedback. We can look at evaporation. All these things we can look at to sort of measure and monitor drought, as well as reservoirs and stream flow. There's a tool out there, probably most of you are aware of this. This is the U.S. Drought Monitor, which sort of takes into account all those different types of indices and actual variables to establish a an assessment of what the drought conditions are like. And this is actually the most recent one, and the California drought is continuing. Exceptional drought. It's just in California not too long ago, and it's getting dangerous for a lot of the folks that live out there in terms of the water resources and the availability of water resources. Last couple of years, there's been significant drought across the Great Plains. For the most part, that's been eradicated. There's a little bit of dryness and drought formation across the East Texas and western Louisiana that's occurred in the last month or two, just due to limited precipitation. Of course, if we have what we think we're going to have with El Nino this year, that could change how this whole U.S. Drought Monitor looks in a pretty short duration of time. Certainly, the short-term drought that's developed across East Texas could be eliminated due to above normal precipitation that we would expect in that time frame associated with the impacts of El Nino. Also could have a significant dent in what's happening out here in the western portion of the United States. Of course, drought development is not just sometimes there's large-scale drought and sometimes there's small-scale drought, and sometimes drought can develop pretty quickly. One topic that's sort of becoming more popular is sort of something like flash drought. So I've highlighted two circles here. The one on the left is July 3rd of 2012, and it was abnormally dry in the region, and then within about 4 to 6 weeks some of the portions of the region had transitioned into exceptional drought conditions, and it basically did so rather rapidly, very rapidly. And this is the evolution of drought is one of those features that's gaining more attention in terms of us trying to understand the processes that drive these features. And that actually seems to be very tied on not just to the larger scale atmospheric pattern, but the ecosystem, the amount of water that's in the soils, and then how vegetation uses that water as it becomes more stressed. So that's actually a topic for another discussion at some point if you want to learn more about flash drought and its development. I don't know if I'm going to make my time period here, but looking at drought and drought conditions, because Amber is giving me the 10 minutes left signal, and who knows how long ago that was, but I'll try to roll through this a little bit. Drought itself changes, as I've mentioned. This is just basically looking from January of 2011 to October of 2014, and you can see how drought in the Great Plains area sort of shifts. And in 2011, it's in the southern Great Plains. And in October of 2012, it's really central. It's evolved to be more of a central and northern Great Plains type of drought. And then you see a waxing and a waning of these drought types of events and drought periods. And then by July of 2014, it was settled really significantly over the southern Great Plains again, especially places like Wichita Falls. Wichita Falls in April of this year, Wichita Falls and Lawton in April of this year began cloud seeding because the reservoirs are gotten so low, and some of that's similar to in and around Wichita Falls. And then May of this year happened and filled it all back up. So $500,000 invested and obliterated by the atmosphere in less than a month. Just a sort of point of reference. So getting back to the study, and I'll try to walk you through this as with the time I have left. The study that we did was to look at these changes from drought to above normal precipitation, like what we saw this year. How often does that happen? What maybe, and sort of give us at least a starting point for assessing some of the impacts and the drivers of these types of events. So as part of this study, what we did was we looked at the long-term climatology and a yearly basis. And we were looking at the water year. So to have a consistent record, we were looking at the water year. When did we see these significant changes on the water year, basically beginning in drought and then ending up in a significantly above normal precipitation pattern? And each of these blue lines going back basically to the late 1800s going through to 2013, each of these blue lines represents one of these, statistically, one of these drought to pluvial periods. Now, some of them look like they should be, but like, for example, this one that I'm highlighting here in the early 1900s, this one is not, because it started off as a pluvial and just became more of a pluvial. So we're interested in these that start below the line and basically end up above the line and significantly above the line. In some cases, they didn't make the cut. Some other cases, like this particular case, let me use a different color here. This particular case is actually taking place over a couple of years, not over one particular water year. So how often did we have these where you're in the middle of a drought and then all of a sudden it starts raining basically cats and dogs? And so if we look at this climate division 2, which represents north central Oklahoma, we can see that there are a number of these events that happened in the climatological record, basically going back into the late 1800s. What's also really important is to, if you take a look at this and divide it up, there's definitely a difference, say going back to 1950, where there's definitely more of these types of events that have occurred since 1950 than what happened before 1950. So this is an important starting point. Yes, there are these events that happen. It's not just in these windows of the 1956, the 1957 drought to pluvial period, which is very significant. They happen in other years, for example, 2006 to 2007. Here in this particular climate division, but also, and even in slightly smaller magnitudes, going back into the climatological record. What's also as important is that they appear to be increasing with time. And there's another way you can also sort of look at this, is it's a more holistic type of analysis, and instead of looking at just drought to pluvial, more of a standard deviation type of analysis. But basically the same thing holds true when we take it from climate division and perform a slightly different set of statistics on it, take it from climate division to the Southern Great Plains, divide it from 1950 and forward, you end up having more of these types of events that are happening, and these are just significant precipitation anomalies from year to year. So some of these that were really drought and didn't even quite make it back to pluvial, but were significant changes in precipitation from one year to the next. They're happening more in the latter half of the time series than they happened at the beginning. So again, we get back into this question: what's driving these types of events? Why are they becoming potentially more frequent? What are we seeing in the climatological record that could be driving these processes forward? But it's also important from a caveat. That, if you're in the middle of a drought, what's the chances of of having a year the following year that's not drought, that's really significantly wet from a precipitation standpoint? And if we look at these three domains, in the Southern Great Plains, it's actually more than 1 in 4. So if you're in the middle of a drought, let me be clear about this, you're currently in the middle of a drought, there's a 1 in 4 chance that the following year, at least a 25% chance based on the climatological record, that the following year you won't even just get the normal, you're going to get well above normal precipitation. That's a tough sort of concept to wrap your brain around, that we're not just going to see rainfall next year, but above normal, abundant rainfall. And looking at these regions in the Great Plains, you see that it basically is about a 15 to 25% over these large-scale domains. What's important is the analysis also point out when you get down to individual climate divisions that these numbers can jump into the range of 35, almost 40%. So you could be in drought one year and you have a 35% chance, a 1 in 3 chance at least, of being in an above normal precipitation pattern, significantly above normal precipitation pattern the following year. So these shifts in precipitation can be pretty dramatic. In some ways, they're almost predictable. When do these shifts tend to happen? That was another thing that we were curious about is, when are you most likely to have a month with abundant precipitation during these changes from drought to well above normal from year to year? And what we found is that it is different. The Amber's telling me I have 1 minute left, so I'll try to wrap this up. But when we get into the details of this, in the southern Great Plains, our most likely months of actually replenishing water during these pluvial years is to have a wet winter. That's one mechanism, and this could be sort of your El Nino impact, maybe, especially, but maybe more this window of time could be more of an El Nino impact. But basically, sort of getting into that cool season, the cool season months tend to be the months that are most important for generating above normal precipitation months. Notice that May in the southern Great Plains isn't exactly typical of a pluvial month, but this year it was. And so, again, we get into that interannual seasonal to interannual variability, what's driving the processes. In the northern Great Plains, it's actually pretty clear that it actually is May. So maybe we can learn a little bit about the May of this year and compare it to other northern Great Plains events. Maybe there's similar features that are providing it, or maybe there's other dominant features. In the high plains, it's actually September. And if you look at the high plains, September actually tends to be a really wet month, and years that you get really significant flooding in the high plains, especially the Lee of the Rockies, it tends to be at the tail end of the North American monsoon. So that gives us some ideas of where to search for some of those answers. So at this point, I think what I'll do is just wrap up our study results, which are that for the larger regions of the Great Plains, there are these changes. We've seen these changes from year to year. There's significant changes. They're likely due to a number of different complex features. But it's really interesting that you can be in the significant drought and have just across the whole domain, have a 1 in 4 chance. But in individual areas, it may be a 1 in 3 chance of not just having rainfall the next year, but we're having abundant rainfall the next year. It's also interesting that some of these transitions from significant drought to significant pluvial episodes have been increasing with time, and that sort of makes us pause in terms of looking at our climate of what are the drivers that might be causing this. Are we ending up with more significant, heavier precipitation in these regions and more precipitation extremes? And that's where we get into sort of the last couple of slides, which may be something that's relevant for a future webinar, which is that there's some impacts of climate change that may be playing a role in some of these features. So I'm going to skip those slides and just get back to the final thoughts for now, and that the Great Plains has a significant variability to seasonal and annual variability precipitation. And there's many drivers for the variability that exists in the region, and really we touched on some of the larger scale processes that involve local land-atmosphere interaction feedbacks on seasonal and interannual variability, and then also sea surface temperature anomalies across the globe. What we haven't really talked about are some of these small-scale processes, and you can sort of ask the question, what drives heavy rainfall on the weather scale? We haven't really talked about that, and so I'll talk to Amber, and maybe we'll do an upcoming webinar really on heavy precipitation and flash flooding in this region in the Great Plains. But I think it's also really important to note that there are just many unknowns that still exist and require additional study. And so that's a topic that we need to continue to follow up on. We've got additional studies myself, but other people are working on this as well, because the Great Plains is an important component of our socioeconomic system, and impacts in the weather climate system here have feedbacks into many aspects of our lives. Not just for those who live here, but those who live beyond. So there's plenty of work to do in terms of understanding these processes. So with that, I think we'll end here with questions, if there are any.
All right. Well, I don't have any questions in the chat box. If anybody wants to add those, we'll give a couple more seconds, and otherwise we will conclude today's webinar. Our next webinar is on September 21st at 1 p.m. Dr. Brian Arnold will be talking about the use of enriched strips and active sensors for nitrogen management to reduce risk and increase profits. I'll be sending out an announcement with a registration link for that webinar. If you registered for this webinar, you are on the mailing list to get that announcement. It should be coming out in the next week or so. Otherwise, have a good afternoon.